So now the condition 2, we can go back to condition 2 here. So we can see here what is our condition 2, what we want to prove. We want to prove they have the same centroid. So both the system have the same centroid. Okay, so we are taking here, we'll take, let G1 H1 and G2 H, we are taking here, let G1 H1 and G2 H2 be two parallel lines. Okay, we are taking two parallel lines, each perpendicular to G1 G2, and let I star be the moment of inertia of either system about a line lambda. Okay, about a line, about the line G1 H1. Okay, about the line G1 H1, the moment of inertia. Okay, so moment of inertia about the line G1 H1 is given to be I star, and this is perpendicular to G1 G2. See, we have taken two lines. We are taking two centroid for both the system. G1 is the centroid for the first body, G2 is the centroid for the second body, and we have already proved in the condition 1 they have the same mass. So the mass of this is also m, and the mass of this is also m. So here I'm taking two lines, so G1 H1 and G2 H2, and we can see that both the lines are perpendicular to G1 G2, and these two lines are parallel. So we'll try to find moment of inertia of the first system about the line G2 H2. So we are going to find moment of inertia of the first system about the line G2 H2, and we are taking this. Okay, we know this. The moment of inertia about this line is what? It is I star. Okay, so we can use the parallel axis theorem. So moment of inertia about this line will be, suppose I donate as I, or if you don't donate, if we donate as I, okay, or I1, if we donate as I1, for example. So by using parallel axis theorem, okay, by using parallel axis theorem, we have what? I1 equal to moment of inertia about H1 G1, that is I star. Okay, I star plus mass. What is the mass of this? M. Okay, and the distance between them is G1 G2 whole thing square. So that is the moment of inertia of the first system with respect to G2 H2 or G2 H2. Yeah, so I think you understand this. Now we'll try to find the moment of inertia of the second system about G2 H2. Okay, G2 H2. So suppose if I take, for example, I'll take here, I want to find about this. So suppose I take the moment of inertia about this system. Okay, suppose I take the moment of inertia about this line. Okay, this line has to be I1, because we have taken this one as moment of inertia about this line to be I1, and this line I am taken as I star. So suppose I take this one as I1. Okay, so I'll try to find what is the moment of inertia of this system about G1 H1. Okay, so G1 H1 will be what? By using the parallel axis theorem, we'll have what? I star. Okay, I star equal to I1 plus M, mass of the system is M, and the distance between them is G1 G2 whole thing square. So, but I want to find about G2H2. So G2H2 is what here? We get here what? I1 equal to I star minus M G1 G2 whole thing square. So that is the moment of inertia of the second system about the line G2H2. That is I star minus M G1 G2 whole thing square. So that's why we get here moment of inertia of the second system about G1 G2 H2 is nothing but I star minus M G1 G2 whole thing square. Now these two systems are equimomental, so the moment of inertia about any line in space should be equal. So we are finding about G2 H2 for this also and this also. For both the system we are finding about G2 H2 and G2 H2. So these two moment of inertia should be equal. So if we take these two moment of inertia equal, what you get here? We're getting here I star plus M G1 G2 whole thing square equal to I star minus M G1 G2 whole thing square. So I star and I star get cancelled. So bring this one to this side, we get 2M G1 G2 whole thing square equal to 0. But this 2m cannot be 0. 2 is a constant, it can never be 0, and mass is also a constant, so it will not be 0. So we have g1 g2 whole thing square is 0. So we get that g1 g2 is 0. So this is possible, this thing, because g1 g2 is a distance. So the distance is 0, that means these 2 points should coincide each other. So that's why we have here g1 will be equal to g2, and which is equal to g say. Hence we have proved that both the system they have the same centroid. So let us prove now the condition 3. Condition 3 is that they have the same principal axis and the principal moment of inertia about the centroid. Okay, since the two systems are equimomental, so by the definition we can say that they have the same principal axis and the principal moment of inertia. As both the system, okay, as both the system have the same moment of inertia about any line through their common centroid, so that's why they have the same principal axis and the principal moment of inertia about through the common centroid G. Because we can see that since the system are equimomental, they have the same mass. Okay, first of all, they have the same mass, they have the same centroid. Since they have the same centroid, so the moment of inertia about any line through the centroid will be equal. So that's why they have the same principal moment of inertia about any line passing through the centroid, and as well as they will have the same principal axis at the centroid. Thank you.